In this lab, we computed the electric force as well as the electric charge acting on a piece of tape from another electrically charged piece of tape. In order to do so, we found the length of both pieces, the mass of both pieces, and the distance between the pieces when one was floating above the other. This allowed us to compute the gravitational force acting on the tape as well as the electric force coming from the bottom tape onto the top tape. We computed the charge using a line charge model by dividing the tape into different point charges and computing the electric force at each point. Important physics principles in understanding the mechanics of this lab are Newton's second law because the tape has a momentum of zero, meaning that the overall net force is also equal to zero because the tape is at equilibrium. Also, superposition of charges is important because each charge on the bottom tape has a corresponding force on a point charge in the top tape. Also, electric field of distributed charges because the charges distributed across the tape each emit electric force that has an overall net electric field. I found that the charge from the computational line model in this lab had a smaller magnitude than the estimation made by calculating a single point charge on the tape. In order to compare the line charge model to the point charge model, we have to use Newton's second law and Coulomb's law in order to approximate the charge. With the measurements of a mass of 2 times 10 to the negative 4 kilogram and a distance between the two tapes when the top tape was floating of 0.026 meters, we can plug these values in order to solve for Q, the charge on the tape, which was found to be 1.21 times 10 to the negative 8th coulombs. Important assumptions to make these calculations are that we can ignore air resistance on a moving object, and for the line charge model, we can assume that each U-tape has about the same amount of charge evenly distributed along the length of the tape. These calculations assume that the charge is concentrated at a single point on the tape, but in the following model, we will see how to approximate the charge distributed across the length of the tape. In the bottom left corner, you can see the display that is the result of the line charge computational model found through coding. The red dots represent the line charge of the top tape, and the blue dots represent the line charges of the bottom tape. The smaller green arrows are each showing the electric field emitted by the bottom tape on the top tape point charge. The large white arrow is the net electric force that is the result of all of the individual electric fields from the top tape. The yellow arrow is the gravitational force that is also acting on the top tape, and that is the same for across the tape. On the right-hand side, you can see the snippet of code that best shows how this was achieved. You need to iterate through each of the charges on the top tape, and within that, the charge on the bottom tape that corresponds to it, and calculate the electric field on the bottom, from the bottom to the top charge. Then you can sum them up to ultimately find the net electric field at the top due to the bottom. You can see that the magnitudes of the electric force and the gravitational force are equal, which is where Newton's second law comes into play because the top tape is at equilibrium. The charge that corresponded to these matching electric forces is 8.44 times 10 to the negative 9 coulombs. This differed from the computation for just the regular point charge, which was 1.21 times 10 to the negative 8th coulombs. If they had been modeled as point charges, just like in Lab 1, the charge found would have been exactly what was predicted, rather than larger than the line charge calculation that I did find. These estimates are different because the line charge model is more accurate. Breaking up the charge into smaller pieces and finding the force at each piece based on the corresponding charge gives a more correct result than simply calculating one force and assuming it is consistent across the entire piece of tape.